What's up everybody, and welcome to part 14 of my basics of deep learning series. In the previous video we implemented the backpropagation algorithm code, and then we executed one gradient descent step, and with that we could reduce our mean squared error by some small amount. But because the improvement was only so small, that means that we have to make many more gradient descent steps. The question is, how many should we do? Or more generally speaking, what does the learning process of a neural net look like? And this is what we're going to cover in this video. So since our initial goal was to find such weights that the mean squared error would be minimized, a simple approach for making sure that the neural net is able to make correct predictions is to simply monitor how the mean squared error changes over the course of doing many gradient descent steps. And this way then we can see how it behaves and then accordingly adjust maybe the learning rate or our neural net if that is necessary. So this is what we're going to do. But before we now get into the code, let's first think about how the mean squared error should ideally behave when we execute the gradient descent steps. And therefore, let's again look at a simpler function than the mean squared error. And this function is again going to be simply x squared. So here I have executed a couple of gradient descent steps with a learning rate of 0.2 and the starting x value was 5. So as you can see, we reached the minimum of this function, or at least it seems like that we reached minimum, because if I print out the steps that we have taken, then you can see here this last step is actually at 0.03. So we are only somewhere close to the minimum and not actually at the minimum, which would be 0 in this case. Okay, so here in this plot I have charted how this function changes over the course of our gradient descent steps. So at step 0, so at our starting point where x is 5, the value is then accordingly 25. And then with each gradient descent step, the function gets smaller and smaller until it almost reaches 0, and then we can stop our training process. And this is what ideally the learning curve, or the curve of the function, in our case then the curve of the mean squared error, should look like. In the beginning there should be a large drop off because we're taking large steps towards the minimum, and then that decrease should taper off until it eventually flattens out and we can then stop the learning process. So this is what we are looking for. But now let's see what happens to this curve here when we take a smaller learning rate, or when the learning rate is too small. So let's set it to 0.002 and let's see what happens. And in this case, this learning curve here is basically linear, and this is a clear sign that the learning rate is too small. And also here you can see that we barely moved away from our starting point. So what we could now do, however, is to simply take more steps to get closer to the minimum. So let's, instead of doing 10 steps, let's do 100. And now as you can see, this curve here seems to bend a little bit, starts to bending. So it seems to be moving more like into the shape that we want to see. And here you can also see that we got closer to the minimum, but we are still far away. So let's do even more steps. So let's do 1,000. And now this learning curve here basically looks like our ideal shape. And here we have reached basically the minimum. So clearly there seems to be a trade-off between the learning rate and the number of gradient descent steps that you need to do. So in this case, with a learning rate of 0.002, we can still reach the minimum, but we needed 1,000 steps to do that. Whereas with a learning rate of 0.2, we just needed 10 steps to do that. So you might be tempted to even choose a higher learning rate than 0.2, but you also have to be careful with that, and let's see why. So let's set the learning rate to 0.9 and then let's just do again just 10 steps. And here what happens is that this curve here basically looks like our ideal shape. And here, when we do this, the descent steps, gradient descent steps, we actually then overshoot the minimum, but we land somewhere lower on this curve here. And then we overshoot it again, and this way we get closer and closer to the minimum. And if I print out those steps, then you can see, however, that this last step is at 0.53. So we are further away from the minimum than we were before, where we just had the learning rate of 0.2. So a higher learning rate doesn't guarantee that you will get faster to the minimum. And it can even be the cause why you will never reach the minimum. So let's set the learning rate even higher. So let's set it to 1.1. And let's just do 5 steps. And let's see what happens here. And here what happens is that we overshoot the minimum so much that we even land up somewhere higher on this curve than we were before. This just keeps escalating. So our learning curve, our curve of the mean squared error, actually doesn't decrease, but it increases. So that is a clear sign that the learning rate is too high. So let's set it back to 0.2, and let's do again 10 steps. And now to recap, as a general rule of thumb for the training process, you want to balance out the learning rate and the gradient descent steps. The learning rate should be basically as high as possible so that the gradient descent algorithm runs as fast as possible, but the learning rate should also be as low as necessary so that you actually reach the minimum. And as another rule of thumb for the training process, let's say you would have a curve that looks like this, that has this shape, but instead of going down to almost 0, let's say it tapers off already at 5 or maybe even at 10. In that case, the neural net simply seems to be too small to learn the patterns in the data. So because you can't decrease the cost function close to 0. So in that case, what you can do is then simply increase the size of the neural net. So for example, adding more layers or adding more nodes within the layers. So this is what the training process generally looks like. And now let's implement it in code. So let's get back to this notebook. And here let's first put this equation for the mean squared error into its own function. And here I've already done that. And another thing that I did was to split the data into a training and testing data set. That way we can then see if the neural net can also classify new unknown flowers that it hasn't seen before, that it wasn't trained on. So now let's create a dictionary with which we're gonna track the mean squared error over the course of the gradient descent steps. So we're gonna say monitoring equals a dictionary where the key is the mean squared error, and then the value is simply a list. And now actually, since we're doing a classification task, so we want to classify a particular flower, what species it is. So let's also track or monitor another metric, which is going to be the accuracy. So we're going to say accuracy, and here also an empty list. So now let's create another helper function that calculates the accuracy. So we're going to say accuracy, and here we put in the predictions and the labels, and then obviously it should return the accuracy. And to understand how the function should work, let's now create a predictions variable. So I'm going to say predictions and we simply take the first 5 rows of our output layer outputs, and let's print them. And let's do the same thing for labels. So here we're going to take the first 5 rows of our training labels, and then let's also print those. So as you may remember, we have 1 hard encoded the labels. So if the 1 is in the first column here, then the flower is an iris setosa. If it is in the second column, then it's an iris versicolor. And if it is in the third column, then it's an iris virginica. So the way that we're going to do our classifications is that we look for each row where the highest value is, and that will be then our classification. So in this case here, the highest value is in this last column, so this flower we would classify as an iris virginica. So now to do those classifications, we need to know in which column the highest value is for each row, and that we can get by saying predictions.argmax and then axis along the axis 1. So in this case, the largest values are always in column 2, so always in this column. And then we can do the same thing for the labels.argmax axis 1. And here we can see for the first row, the highest value is in column 0, then in column 2, then column 1, and then column 0 and 0. And now, to know which of those predictions are correct, we simply compare these 2 arrays. So we can copy this, paste it, and then equals this array. And here we can then see, okay, the second classification was correct. So this one where we set 2, and it was actually a 2. The largest value was in column 2. So this Boolean array here we can store in a variable called predictions correct. And now to finally calculate the accuracy, we can then simply calculate the mean of this Boolean array, because trues are treated as a 1 and falses as a 0. So if we do that now, mean, we get an accuracy of 0.2, and that's because one of those 5 predictions was correct. So this is going to be then the accuracy. So that's how the function is going to work. So let's copy this and paste it into here. So that are our helper functions. And now let's start with the gradient descent algorithm. So therefore what we want to do is we want to run this code here many times. So we're going to put it into a for loop. And in the context of deep learning, an iteration of such a for loop is called an epoch. So we're going to say epoch for epoch in range epochs. So in the parameters here, let's create a variable called epochs, and we're going to set it to 1000. So now to monitor the training process, let's create another comment. So we're going to say monitor training process, and we're going to say MSE equals mean squared error of our output layer outputs and the labels, so y train, and then the same thing for the accuracy. So again, output layer outputs and y train, and then we store those values in those lists here. So we're going to say monitoring mean squared error dot append the mean squared error, and the same thing for the accuracy. So accuracy append the accuracy. So that's basically it, what we have to change. And then at the end of the for loop, we're going to transform this dictionary into a data frame. So we're going to say monitoring underscore df equals pd dot data frame of our monitoring dictionary. Okay, so let's run this and let's see if it worked. So let's print out the data frame, and as you can see, it worked. And now we're gonna plot how the mean squared error and the accuracy changes, how they change over the course of the different gradient descent steps. And therefore, we're gonna create some subplots. So I'm gonna say figure, comma axis equals plt subplots, and one row and 2 columns, so they are side by side. And then we're going to set the figure size to 15 and 5. So those are our 2 plots. And now in this first plot here, we're going to put the curve for the mean squared error. So we're going to say monitoring df dot mean squared error dot plot, and then x is axis 0, and then the title is going to be the mean squared error. And then we want to do the same thing for the accuracy, so let's just copy this, and then here we're going to say accuracy, this is then 1, and here we're also going to say accuracy. So let's see what that looks like. And here our accuracy does some strange behavior, so it bounces back between an accuracy of 65% and 35%. And here the mean squared error is still pointing down, so we haven't reached the part where the curve flattens out. So let's do another 1000 steps. So let's run this here again. And now let's see what that looks like. And now the accuracy kind of stabilized above 65%, and the mean squared error is still pointing down. So in this case, we could now maybe think about increasing the learning rate, but let's just do some more iterations, some more steps. And this time we're not just going to do 1000, so let's do 10,000 steps. And let's run this cell again, and now let's see what that looks like. And here the mean squared error now basically looks like our ideal shape, and the learning rate, the accuracy climbed almost to 1.0, and it even looks like that it's still going up. So let's do some more iterations, and let's do another 3000 so that we get to 15,000. So 3000, and let's run it again, and let's see what that looks like. So it hasn't really changed much, so accuracy has stabilized, and the mean squared error curve also went down somewhat more, but I think now we could stop the training process, and let's see how the neural net classifies the flowers from the test data set. So let's create another heading. So we're going to say test data, and then let's just copy the feed forward code, put it into here, and this time obviously we use the features from the test data set and not the training data set. And then let's also calculate the accuracy. So we're going to say accuracy of our output layer outputs and the labels from the test data set. And then let's also print that. So we're going to say accuracy colon and placeholder, and then dot format accuracy. So now let's see how good the neural net is at classifying those test flowers. And here we get an accuracy of 95%. So clearly the neural net has learned to distinguish the different types of flowers. And now, before I wrap up, let's see how the neural net learns when we use a different train test split. So we're going to set the random state to 7. And let's also choose a different starting point for our weights. So here we're gonna set the random seed to 3. And then let's also do a total of 15,000 steps. So here we're gonna say epochs 15,000. And now let's train the neural net on that and let's see what that looks like. And here now our curve basically looks like our idea shape, but it already flattens out at 0.111. So it didn't really get so close to 0. And you can also see this in the accuracy. This is shortly under 35%. So basically it's guessing randomly. So for some reason in this scenario, maybe because of the different train test split or because of the different starting points for our weight, the neural net wasn't able to learn the patterns from the data. So now how to solve this problem, we can refer back to the second general rule of thumb that I mentioned before for the learning process, which was that in this case, when the curve flattens out and we are still far away from 0, then we might consider increasing the neural net, and this is what we're going to do. So we're gonna, however, not add another layer, because then we would have to alter too much of our code. So let's just increase the nodes in the hidden layer, and we're gonna set it to 6. So now let's see how the neural net learns in this scenario. And now the curve again looks like our idea shape, and it went down to below 0.02. And the accuracy is again very close to 1. So now let's see how this neural net classifies our new unseen flowers, so the flowers from the test data set. And here we get an accuracy of 90%. So clearly, also in this scenario, the neural net was able to learn how to distinguish the different types of flowers. And with that now, we have basically answered those two questions that we posed in the first video of the series, namely, how does the deep learning algorithm make a decision, and how do you determine the right parameters for the algorithm? So now we have basically reached the end of the series, but let's do one more video, namely, so to say, as a summary of the whole series. In the upcoming video, we are going to code a neural net from start to finish for a different data set. And the data set is going to be the Titanic data set. So thanks for watching, and hopefully I will see you in the next video.